we build a tree, we basically take the things that are the least used and we create a new node that represents those, and we make its two leaves the things that are the least useful in our list. So we'll look at the example that they have. So basically you need to go through all the text that you have. You need to figure out what are the frequencies of everything, right? So you figure out how often they are used, or, well, not used, but how often each one of them are used, and you build up a frequency chart that has them. So let's do an example. All right, so if we think of every item that is in this as a node, right, we can draw them as, I have an X, right? I have an X node, its weight is 1. I have a U node, its weight is 1. I create a XU node, its weight is 2. Right, so I build that up as a tree. And each one of these I'm going to put into a list that I have, sorted by how frequent it is. Right, so it has a weight of 2. We come here and we look at our list, and if our list is sorted by the weight, we would create a P and a R node, right? Because P has a value of 1, R has a value of 1. Together, PR has a value of 2. Right? So we're building this tree. So those have weight of 2. Perhaps I should draw it better on the bottom here. PR, this node is 2. UX has a weight of 2. Right? LO has a weight of 2. And then we have a bunch of things that have weight of 2, so I could pick any 2 of those. So now maybe these 2 nodes are combined, right, to make one that has 4. Let's see, I got a T. It has a 2, so I can make these, and I get a node with 4. Let's see, I could combine S and N. M and I. Right, and eventually then I'll take maybe these 2 nodes will get combined to one that has 8. 8. And then it looks like I have a space is one that has 7. So you just keep combining the things that are the smallest together. And then what we do is we generate an encoding based on the fact that if we build this entire tree, if you go left, it's a 1, and if you go right, it's a 0. Or vice versa, right? It doesn't really matter which way it is. And so you end up with a variable length. So the length of the encoding for a particular letter, so let's suppose that this is our full tree right here, just for the sake of example. So if we go this direction is a 1, this is a 0, this is a 1, this is a 0, 1, 0, 1, 0. Right? So if we look at, I think it was a P and a R, right? The encoding for that is the set of nodes that we traverse going down this tree, right? So an R is a 0, 0, 0. A P is a 0, 0, 1. Right? But if we have something like this, T occurs sort of more than, right, any of these single ones, right? So its encoding is just 1 to 1. Right? So it has an actual shorter encoding than all of the rest of them because it occurred more frequently than all of the rest of those. So you can take any set of text and you can build a Huffman encoding for that set of text. So that way when you're transmitting it, you can say, well, if I send you a 1, 1, you can take your tree and you can figure out, well, if I go 1, 1, I end up with a T. And then if you see 0, 1, 1, well, we know that if it starts with a 0, right, it's got at least, we know that it's on this side of the tree, so we can figure out how long we need to look. Right, so basically we just keep going down the tree until we hit a end node, right? And then we go in and we'll parse the next one. So that 0, 1, 1 would be a U, right? So we got a T, we got a U. Maybe we have 0, 1, 0. And that would be a X, right? So why might we want to use this type of encoding? Can there be any benefits to using this? If I was going to represent these in ASCII, how many bits would I have to use? Or Unicode? How many bits are in ASCII? 8, right? ASCII uses 7 of the 8 for printable characters. They use 8 bits, right? So here I just used 8 bits and I transmitted 3 letters, right? So you'll use a type of encoding in order to send data, and what we're doing is we're compressing the data, right? So compressing, there's 2 different types of compression. Anybody know the different types of compression? General types. If I make a JPEG, is that as good as maybe a different type of format? Does anybody think of a type of format that's better than JPEG? PNG. Why is PNG better than JPEG? Keywords. We'll just yell out random keywords. Yeah. Big data, Oracle, Java, computer. I always like it when they do things and they say, the computer has a brain. No, it does not. You know any of the different types of compression? General types? Let's learn them.
Oh, lossless and lossy.
Lossless and lossy, right? So in lossless compression, we don't lose any data, right? If I take a bunch of files and I zip them up and send them to you, right? We don't want to lose data, right? We want all the data to get there. Right, so there are a couple different file formats. So JPEG is one. So JPEG does do compression and does lossy. Right, so you actually lose data when you compress it. Whereas PNG, TIFF, right, tagged image file format. On your digital cameras, they'll have 2 different modes. They'll have like JPEG mode and they'll have what's called RAW mode. So I shoot all my pictures using RAW. So RAW is you take the actual just sensor data. For every pixel that it sees on the sensor, right, it records what value did that have. Right, and it's not a normal format, it's just the whatever native to your particular camera. So mine is a Canon, so it's like a CR2, Canon RAW version 2 that mine produces. Right, so you can use either one of these and there's benefits to them, right? So if you have lossy, you're removing data, but you're also making stuff a lot smaller, right? So your pictures take up less space. When I take a raw picture with my T5i, right, it's like 15 megs for each picture. If I take it with JPEG, it's 3 or 4 or 5, depending on how much variance there is in color between all the different pixels in my image. But then I can go and print off an 8x10 and I don't have to worry about losing stuff. Okay? So when I'm sending you data and I want to make it smaller as I'm sending it to you, right, I want to use a lossless compression algorithm. I want to use something that you don't lose data, right? Another one is it's called deflate. So deflate is what's used in PKZip, and I think zip, right? zlib, LZ77. Right, so the deflate is actually used when if you look at making an internet connection, right? You'll sometimes see that it's going to use deflate compression, which actually uses Huffman encoding, right? For the part of the deflate, right? Is this Huffman encoding? Right? So basically what it does is when you're setting up a connection with one of these, it goes through and analyzes the frequencies of all the letters, and then basically sends you hey, here's a tree that represents what the encoding is going to be, and then it starts sending you the encoding, right? So it sends you the encoded letters. So you're going to have a little bit of overhead of sending that tree over the wire, but if you're sending a lot of data, if you can reduce the bits down from 8 to maybe 3 or 4, like in our example, right, that's going to save you bandwidth. And as long as we recreate everything appropriately, right, stuff will be okay. All right? So it's actually used, and if you ever do a packet capture, you might see that it's going to use deflate compression for that. Or if you use the standard tools for zipping up stuff. Some people like 7-zip, which uses a different algorithm, but it does a really good job of compressing stuff. Any other compression algorithms we can think of? You guys have seen? Gzip or tar-gz, right? So gzip will just do a single file. And does anybody know what tar stands for?
Tarball.
Well, tarball is a tar-gzipped file. You got to think old. Something starts with a T. Something that's old, it starts with a T. That you might use in your old car to record stuff off the radio. Tape! TAR is for tape archive. So what they would do is they would take a bunch of directories and files, and they would put them all together in a format where instead of having a directory and a bunch of files, you have a single file. Right? So we put them all together in one file. And actually, it's really easy to do. So I have a bunch of PowerPoints here. So if you don't know how to use something on the command line, remember what we type? Man. Right? And we can give it a bunch of options, right? If we were writing ourselves a shell, right, we can pass it a bunch of arguments, right? So -C is for create. I want to create a new archive. Let's see, V is for verbose. I think it'll tell you what it's doing. F is for file. I don't see it directly here. Yep, F for file. And then Z, see if I can find Z. We'll compress it, right? So if I tar something, I make it into one file, and then I can compress it at the same time. So instead of running 2 commands, right, we actually take the output of one command, and we can pipe it to the input of another command, and we can zip it. So I can say tar CZV for verbose, so we'll print off stuff. F, and call this bob.tar.gz. Right? So the Z or V will print off for us all the files that it's adding to the archive. Right? The C is for create. I'm going to create, and the first argument that you give is what you're creating. The second argument is what are the things that you're going to put inside of that. So I'm just doing PowerPoint, so it'll do all the things inside of PowerPoint. So now if I do an ls, and actually this is probably getting uploaded to the cloud, so all right. Right, we can see that I have a file called bob.tar.gz. And if you want to extract it, you can say tar, well, let's go up one directory. Tar zx for extract, vf. You give the name of the archive, which is called Bob, and it shows all the files that it extracted. Okay, so this is lossless, right? We don't lose any data when we do this, but the result is going to be much smaller. So let's see.
What's a conveyor belt?
What's a conveyor belt?
Yeah.
So we were driving down to, so all my computers are named after goofy things that my children say. Right. So we were driving down to Harlan County, and my children, we were talking, and my daughter's like, what's that, you know, Dad, something like, what were we talking about? We were talking about something, and she goes to talk about a conveyor belt, and she said it's a conveyor belt, like Darth Vader, right? I'm like, no, that's not what it's called, but that's kind of funny that you call it that. Also, lightsaber, right? You know, the thing that you attack somebody else with. And then I have Darth Vader. This is another one. There is a Star Wars theme in this, but oh, crud. It's gonna... I forgot. Oh, stupid OS 10. That was cool. Not. Okay, let's look how big this directory is. So the PowerPoint directory is 1.5 megs. Let's see if we did any good by compressing it. All right, that's 1 meg. Right? So not too bad. When I was working, we used to compress our database files. So our database, we would do a full dump of the entire database, get all the contents of it. So when it was tar.gz, tar.gz, it was about 300 megs. And when we uncompressed it, it was 1.5 gigs. So databases have a lot of text. It's very verbose. And so when you run it through a compression algorithm, it does a very good job of making it a lot smaller, right? So it's a third. Bzip is another one. So there's gzip, there's bz for bzip. It actually does better, but it takes a lot longer for it to process, right? So why would we maybe want to use that? Something that takes longer to do the processing? Well, what's the point of compressing it, right? What are the benefits of compressing it? It's smaller, right? So where would be situations where size matters, right?
Every aspect of life.
Every aspect of life. If you're downloading something, right? So the reason why Netflix, right, started off sending people DVDs instead of streaming is because there's a famous quote that says, if I get a truck full of DVDs that has more bandwidth than any internet connection that you can have, right? Think of how much data is in a truck full of DVDs, right? Terabytes, right? To transfer that across the country, it'd be faster to drive it, right? From New York to LA than it would be to try and send it over the internet, right? So if you're gonna send this file over the internet and you have limited connection, like sucky bandwidth like I have at home, right? Making something a lot smaller is going to be a lot better for that transfer rate. So you can spend time compressing it on the front end, and then you don't have to spend as much time downloading it if that download is super slow. All right, so Huffman encoding is something that's useful. It's something that we can build by using a tree, right? Each node in the tree is basically going to have a value that is the sum of its children, right? So this is different than your binary tree where we're trying to sort things. All we care about is building something. And we might make something on the left or right depending on which one is bigger, right? It really doesn't matter which one has a bigger tree. But in the end, right, we end up just building this binary tree that has nodes, right? And each one is either going to get a 1 or a 0 out of the traversal of that tree, right? So as we go down. Okay? So there'll be a couple things that you would have to use, right? So you need to go through and, right, when we're building a Huffman tree, Huffman encoding, right, we need to keep track of what the value of a particular node is, right? And then we're going to have to take two nodes and combine them into a new one and read add them to our list. Right? So, all that great stuff said, right, this is going to be the basis for the next homework that we're going to have, right? So you're actually going to use two data structures that we've talked about in class. One is going to be a list, right, of items. And it'd probably behoove you to have that list sorted according to size, right? And then you're going to build a tree. So basically, I'll give you a bunch of letters and their frequencies, right? So that'll be your input to your program. So it'll be like the example that I had up, right? So you'd get real letters, and I won't put space in there, right? It's not going to be a letter, right? So we'll have A as some number, B as some number, C, right? For a particular set of letters, you'd read that in, build it encoding, and then print off what are the encoded values for each one of the letters, right? So we'd have this table. So your output would end up being A and then the code 010 for this tree. And there will be some trees that will be equivalent, but we'll talk about a rule to make it so that you always put the smaller thing on the left-hand side. So that way we get a deterministic output of exactly one tree for that, or one derivation if we were in automata. Okay? I will try and get that out. We'll probably have about a week and a half to work on that one, right? So we'll want to get started on that soon. All right? And break. We're a football team.